all the way to temperature without being too concerned, right? Because if you think about it, every time that you eliminate the degree of freedom, like a singlet, you put in a singlet with an energy, excitation energy higher than temperature, it's basically like you have a gap, right? If you have a semiconductor and the temperature is much lower than the gap, you don't care about electrons and holes, right? All of these things are going to be exponentially suppressed. So it's the same thing here. Triplet excitations are going to be exponentially suppressed if their energy scale is above temperature. Now, once you bring your energy scale of the Hamiltonian to the range of temperature, right? That means that most of the bonds that remain in the Hamiltonian are over here at very low energy scales. Because by that time, of course, infinite randomness kicked in. This is asymptotically correct. The universal distribution functions are are dominating the behavior. That means that everything that's left in your problem has energies much lower than temperature. But then we know that if you have a quantum system whose energies, whose Hamiltonian just produces eigenstates or eigenenergies that are much lower than temperature, with energy differences much lower than temperature, then you know the temperature will just make all of these states equally occupied, right? It's like they're degenerate as far as the temperature is concerned. The Boltzmann factor is not going to distinguish between them. That is as if the Hamiltonian equals 0. Yes, that's the right answer. Yeah, it's as if the Hamiltonian equals 0. If that's true for Eisenberg model, it's true for anything, basically, that will have infinite randomness scaling. Now, even if it doesn't have infinite randomness scaling, you should say that you're going to RG out high energy degrees of freedom up to the scale of temperature. It just won't be as precise as with infinite randomness. And instead of temperature, so yesterday we used this argument to say that the susceptibility of a random Eisenberg model would go like 1 over d, which is the Curie susceptibility, times however many sites we have left once we reached the scale, the RG scale, gamma, which is log of omega 1 over t. Right? So we eliminated a bunch of sites. Up, we stop here. Whatever we have left, Hamiltonian equals 0. Hamiltonian equals 0. You asked me about the susceptibility of the spin, it's a Curie susceptibility. I could have also asked the same question about magnetization, right? I could have said that somewhere, maybe at a higher energy than temperature, there might have been a magnetic field, right? But then again, my decimation was assuming rotational invariance. We assume that there's no field. If there is a field, this type of argument is always very crude. Either your bond energy is higher than the magnetic field, or it's lower than the magnetic field. If it's higher, then we say that it's much higher than the magnetic field, then it can still form singlets. If it's lower than the magnetic field, we say it's much lower than the magnetic field. Then the magnetic field is just going to polarize. So tell me, what would be the magnetization say if I put my random Heisenberg model in a magnetic field that's much higher than temperature? So think about temperature equals 0 and the dominant competing energy scale is magnetic field. Let's see, what would be the magnetization under these circumstances?
It's the density of bonds underneath that energy scale.
Okay, so we normalize up to this energy scale, and then we say, okay, whatever is left is going to point with the magnetic field because everything else is 0. So then it would be the density at gamma that's about log omega 1 over v.
1 over log squared.
Yeah, 1 over log squared. Some energy scale over v. You see the logic? It's super simple. It's suspiciously simple. But somehow, for the Heisenberg model, it always works. And meaning, the Eisenberg model has this infinite randomness fixed point. Infinite randomness scaling is so good. It's so precise for this problem. And its characteristics are so convenient for calculating physical quantities that we can do all these simple arguments and get rather non-trivial answers. Right? This is a very non-trivial function. So you get the logic? Questions? Yeah.
So how about those functions? In the beginning you assume that all the j's are positive.
Yes.
So then, as long as that's correct, I don't have to care about is Heisenberg or Ising model, or they all get the same distribution, or.
Yeah. So okay. So as long as you start with antiferromagnetic model, what I taught you in the last two lectures would apply to any XXZM Newtonian. So I think if we have like J perp SZ plus J XY S plus S minus plus no, okay, I should be careful. SX SX plus SY SY I plus 1 and so forth. Okay, so this I need to check, but if I recall correctly, if you plot this on J perp over JXY, okay, so what I was discussing yesterday was the critical point, Eisenberg model, where this ratio is 1. XY model is when that ratio is 0. This is free fermions. So for the experts amongst you, this is where you get the Dyson Singularity for free fermions. And I think that this stretches out to -1/4 actually. Can't remember if it's -1/4 or -1/2. So for that we need to check Daniel's paper from '94. But so this, in this entire line, basically, you'll get this random singlet phase. Now, this -1/4, you can calculate it actually without looking at the paper. The point is that all the way from here to here, there's a distinct ground state singlet, right? And actually that continues. The singlet remains the ground state even when J perp is negative. At some point, the singlet becomes the first excited state. And one of the triplet states actually becomes the ground state. So not one of the triplet states, a combination of the triplet states will become a ground state. And at that point, the physics becomes different. And that's the point that's described here. So it's all dictated. As far as I recall, with some caveats, this physics, because of this real space RG, this range is dictated by local physics. By what's the local spectrum of two sites is. And we can calculate it. Now for Leonid yesterday asked me a question about if you have a single impurity, right? If you have a single bond that sucks in your Eisenberg model, then can we see that this order is relevant by seeing that even a single bond that's bad is going to cut the chain off at low energies? So this harks back to this problem of Kane-Fisher, as far as I recall, where the idea is like if you have a bosonized model, like the one that Thierry taught you about, and you make a defect at one point, you can ask about the renormalization, the momentum shadow renormalization of the amplitude of that defect, right? And that defect will be marginal at the xy point. And as you go to the right, it will become more and more relevant. And in fact, I think this point, once you actually calculate the Lattinger parameter of the bosonized model, I think this point is at k equals 2, but I didn't get a chance to check. So it's at the critical, so it's the critical point for it's the same critical point I think that Thierry was discussing. But all this I'm saying is speculation from remembering these things from studying them a few years ago. So you should go back and actually check the connection. And one place to check the connection is Subir's book, where he discusses bosonization of the Heisenberg model in particular. But if that's the case, then you can just take the k equals 2, the Lattinger parameter k equals 2, stick it in the Kane-Fisher result for the scaling dimension of the defect in the metal, or in Lattinger liquid, and see how relevant the defect is. And you'll see that indeed the defect in the chain that corresponds to the Heisenberg model is highly relevant. We'll cut the chain. It has a scaling dimension. So that's, I think Leonid made this comment to say, look, there's another direction from which you can see that even weak disorder is relevant. And that's the limit of the single defect in the Latinger liquid. And it's a very instructive comment. Yeah, Justin.
So when you draw this one-dimensional line, does that mean that you're not varying J perp and Jx, y independently? They have to be tied to each other?
Oh, that's a great question. So it turns out that you can think about two different models, where there's a single coefficient, say here, that depends on site, that makes the magnitude of everything vary together. And that's the easiest thing to look at. And that is, then what I said is precise. If I remember correctly, there's a possibility, of course, of making J perp itself depend on site. And then this would be maybe the ratio of the averages, right? There, I don't think it's known exactly what the phase is. So nobody worked it out. I think Daniel pointed out. I think, again, this is something to look at the paper. But if I recall correctly, the latter model has not been worked out completely as to whether that's the phase or not. Yeah?
Are all the random singlet phases in the same universality class, or do the exponents change?
This is a very good question. So, on the one hand, it's deep. On the other hand, to answer it, one needs to decide what's the terminology and what's the, how do we call the important things. So when I say random singlet, it's strictly this picture of sites connected by arbitrary long-range singlets. You can memorize the monologue that I gave you. Singlets form between nearest neighbors, sometimes between far away neighbors, sometimes between very far away neighbors. If you look at random singlet papers, they always have this configuration of singlets, which makes it not so random. But it gives you the example, right? There's short range, there's long range. I think anytime that you have this configuration and only this configuration, then it will be the same universality class. And here, what do we mean by universality class? So universality class, as Thomas was teaching you yesterday, and as you probably know from before, it has to do with critical exponents, right? It's critical exponents that are the same, regardless of the microscopic details. And here, universality actually means something very strong in addition. It means that regardless of initial distribution, you end up with the same distribution, right? So where are the critical exponents? There was one that I was emphasizing yesterday, you remember?
Psi.
What?
Psi.
Psi, right? So 1 over energy, sorry, log of 1 over energy goes like length scale to the psi. I said that psi equals a half. That's the random singlet universality class. There's another universal number which kind of went under your radar. So, remember the distribution function we got looked like this. Right? There's a number that's not written here. So 1 here. Now you can see it. It's here. That 1 is a critical exponent. Namely, there's actually other infinite randomness fixed points that are not in the same universality class. They have the same universality type of infinite randomness scaling, where there's another number here. And I don't know if we agreed on notation as to how to call the critical exponent. Let's call it chi. And it turns out that as you go to higher spin chains, you can get other critical points. One prominent example is the spin 1 chain. Did you see LTLT models before, some of you? Okay. For those of you who are not, and not even for those of you who have seen it, what is an LTLT model, or spin 1 Eisenberg model? Let me just draw this here. Think of big sites. Each site has spin 1. Spin 1 is how many spin halves? 2, right? Let's draw 2 points in each site. Spin half would be spin 1 would be 2 spin halves symmetrized, right? Now if we make a Heisenberg model out of this stuff, it's very easy to find a candidate ground state, right? If it's 2 spin halves, and you have each one once the sites around it to have minimum spin, what would the ground state look like? Yeah, basically connect all these guys. This stupid argument is actually true. Namely, you take two spin halves in each site, you pretend like they don't talk to each other, you write a state where in each site you get a part, a spin half part that connects to the neighbor. You write this wave function, and then in the end you symmetrize the wave function of the two spin halves to eliminate all the pieces in the wave function that has singlets on each site. And that's a good caricature for the ground state of a spin 1 Eisenberg model. In fact, it's the exact ground state of the AKLTM Newtonian, which is sum over sites si plus 1 plus, I think, 1/3 si dot si plus 1 squared. Yeah, a third is a small number, so this is essentially the Eisenberg model. But this is the exact ground state of this thing. There's no phase transition between having just the Heisenberg model and having this extra biquadratic term. Now this is gapped, right? Because in order to actually excite, you're going to take one of those singlets and make it into a triplet. That triplet can then start wandering around because it's not the exact ground state. It's an excitation that will get a bend. But if you check how much kinetic energy it has relative to how much energy you needed to put in to break the singlet, you find out that the kinetic energy is not enough, and you'll have a gap, which is called, what is it called? The Haldane gap. 0.3 J or so. Of course, there's a famous joke by R. Shankar about what the Haldane gap is. I'm on video, so I shouldn't tell it. But you'll find out one day. Anyway, what I wanted to say is that now you can add disorder, right? You can make all the bonds disordered. And for a little bit, this gap will protect you from destroying this nice ground state. But then at some point, the gap will die. And then at a later point, let's say disorder. At some point, the Haldane gap will die. And then at a later point, there will be a critical point where this feature of a singlet chain crisscrossing through the lattice would go away. And here, at very large disorder, what will you have? Random singlet. Because the disorder is so strong, when you have like a strong bond here, they want to localize as many singlets as it could, right? And you get the same picture. So over here you have a random singlet fixed point, it's stable. Over here you have something that Thomas will teach you a lot about. It's a Griffith space. Now we killed the gap because over here we have a bunch of defects that look like random singlet, but the short scales. But that short scale can be arbitrarily large with very low probability, but that will kill the gap on average. But over here there's a critical point. It's actually a crazy critical point. I'm not going to describe it too much, but I'll just say that it has a psi that's 1/3. It's an infinite randomness critical point, and it has a chi that's 2. So actually it turns out that in general you have those critical points on high spin spin chains that separate between various random singlet type states. And they have psi, which is 1 over 2s plus 1, and chi, which is 2s. As you can see, I feel very strongly about the subject because this was a big chunk of my PhD. Actually, I worked out the spin 3½ case for the analog of the space diagram, which goes from a spin half random singlet to a spin 3½ random singlet phase. But then Keita Dana and David Hughes realized that it's a whole pattern for any spin, and realized that there's a whole set of universality classes of infinite randomness distributions, infinite randomness scaling, which go like this. It's kind of neat. To date, I don't know of a different universality class. Maybe I forgot, but if I remember correctly, there's no other universality class of infinite randomness discovered yet. But they probably exist. All right. Any any questions about this very big tangent? This was all in response to Raoul. Yeah, right.
So if you took some similar model that also had like a matrix product state representation and added disorder to it, would you expect a similar picture?
You know, my guess is as good as yours, but I think it's worth checking. Yeah, but IKLT is like the mother of matrix product states, right? And yeah, so in general, these pictures where you draw random, when you draw singlets like this, nonchalantly, you know, separating light spins into spin half components and so forth, that's called the valence bond solid. So in general, I think disordering valence bond solids in one dimension will result, I think, in one of those fixed points. Certainly for the Eisenberg model type. Any other questions? Yeah?
In the AK phase, if I cut the chain, then I see the edge mode, right?
That's right.
And then does the edge mode survive any other outside of the non-zero gap? Like outside?
Oh, it's a great question.
In the grid.
So I don't know if you know this physics, but it's very beautiful physics, so I'll say it. If you just cut one bond in the AKLT, then okay, then you have to cut this singlet. But everywhere else, the singlets still exist, right? Which means that you'll measure locally what spin? Half, because the other spin half is busy. So this is a great example of fractionalization. There's no spin half degrees of freedom in the problem. Nevertheless, spin half degrees of freedom emerge at the edges. Should hark back to like topological phases. Now, the question is whether, when the gap is closed, whether there's still remnants of this physics of fractionalization. It's worse. That physics of fractionalization enters the bulk. Because now when you ask what kind of degrees of freedom you have in the bulk, particularly at the critical point, say you decimate up to like some temperature or some magnetic field, now you ask what does the susceptibility look like? Is the susceptibility of spin 1, spin half? Right, there's a coefficient in the 1 over t. I don't know if you remember this, but if you calculate a Curie susceptibility, then this 1 over t is actually s times s plus 1, if I remember correctly. Right? And therefore, you know, if s is a half or s is 1, you know, the amplitude is 10 different. Turns out that the fixed point has universal fractions. So the leftover degrees of freedom are universal. Half of them would be spin 1, and half of them would be spin, no, a third would be spin 1, and 2/3 would be spin half. And yeah, this pattern of universal fractions continues for all these fixed points. So this fractionalization enters the bulk, and so you suddenly have tons of spin half degrees of freedom. And you can think about it having many breaks.
So you are talking about spin 1 chain,
Yeah.
and you the wall in between two spin 1 systems.
Yeah, and then you measure spin half. That was actually how this physics was verified. The nickel compound, NENP. Nickel is a transition metal that sits, I think, +2. +2 or minus 2, I can't remember. +2, I think. That means it has spin 1. And they measured with ESR what kind of degrees of freedom you have at breaks between two chains. If NENP, it's a quasi 1D system. It's a 1D system. Sure enough, they found two spin halves interacting very small.
So is your picture sufficient to describe this physics? I mean, you have, rather than spin 1 chains, spin 1 half.
This is actually a precise mapping.
Because
No, this is a precise mapping because the spin 1 is like a triplet. So if you take two spin halves and you eliminate the antisymmetric subspace, what you have is a spin 1. That's precise. And it's a good way of thinking about high spins.
on this direction, I understand. On the opposite direction, I start from spin 1s. So I should be able to have spin 1 halves, unless I have some.
All I'm saying is that if you want to write the wave function for spin 1, you're allowed to write your wave function in terms of spin halves, as long as in the end of the day, you eliminate all the antisymmetric combinations. It's kind of like creating a Fock space, right?
Yes.
You write some wave function for fermions, and then you anti-symmetrize them. Right? You hope to God that you don't have 0 at the end, right? You still have something in your wave function, right? Same here. So this is precise. Gil?
I'm trying to connect to user critical points. At the critical points, do I have gapless things with the fixed point?
Yeah, you're gapless all over, right? Of course you're gapless. Right? You have parallel correlations and you have this spin. You have tons of gapless modes. You have a Dyson Singularity of them. Yeah.
So here, J is the random parameter.
You mean here?
Yeah, that one.
Yeah, I can make it random, but I started with explaining this
Right.
thing for the APLT model, which is not.
What if you make the relative coefficient random?
That's a good question. You can work it out. I think at some point I thought together with Stefan Karen to work it out, but then we got distracted.
Okay.
I think somebody must have worked it out since, maybe a dog. I think either him or a colleague of Brazil, I think, calculated this. But something similar happens. Yeah.
Two questions. One is, what is this Dyson Singularity that you're mentioning?
Yeah, I was wondering what I should say. So Dyson Singularity is the following thing. So if you ask how many low-lying degrees of freedom you have, right, just what's the density of states? Let's see, what's the density of states? Density of states, you want to know the density of states. How would you go about it? So you want to know the density of states at energy E. Let me draw it. E. What do you do?
Differentiate n.
What?
Differentiate n.
Differentiate n. So if we normalize all the way to E, and then differentiate n. So the density of states at energy E should be dn dE, right? Now n is the density at energy E, right? So it's like n naught over log omega 1 over E squared, right? By the way, this 2 here is 1 over psi, you remember? It's universal. Now this thing, if I can still differentiate, goes like 1 over E log E cubed. This looks nasty, right? If I forget about this log, this looks like it doesn't integrate around E equals 0, right? But it actually does because of the logs. Also it should because we got it as a derivative, right? It has to integrate to something. But this form looks like this. So density of states, E. You get crap at high energy, but then as you come close to 0 energy, so now what I'm drawing is density of states of an XY model. Namely, remember I told you to take the diagonalized random hopping? This is what you'll see. It will be a singularity as energy goes to 0. And the divergence is very subtle. It goes like 1 over, this 1 over energy log cubed is very sharp. And because it's an integrable singularity, it's very narrow. So you actually have to focus near the middle of the band to see it. But it's always there. Yeah?
Where is E equals 0 on this plot over there?
On this spot?
Yes.
It will be here.
Here, okay, it will be there.
You're asking me why do I have negative energies?
Yes.
So if you think about the XY model, the hopping, right? So you'll have a band. And in the hopping problem, you have particle Hall symmetry. So really what you're finding is the low energy degrees of freedom, but you're eliminating the deepest bound electrons first, and then you go closer and closer to energy equals 0. But every time that you have a very bound electron with an anti-symmetric wave function, which corresponds to a singlet in terms of the spin, you also have the symmetric wave function with the same energy but with the opposite sign. And so for the XY model, this corresponds to having the singlet as the lowest energy state, the m equals 0 triplet as the highest energy state, and the up, up, down, down as no energy state. This corresponds in fermions to having a symmetric, depending on the signs that you put in the Hamiltonian, a symmetric superposition between two sites, that's a low energy state. Antisymmetric superposition will give you the same energy but with a positive sign. And having two fermions just stifles the hopping. Having no fermions also stifles the hopping. That's the up, up, down, down, zero energy. So when you diagonalize, you'll get both, right? And you'll see that. That's the Dyson Singularity. And sorry for not telling you about this before. I'm being a little vague, not vague, but just disorganized about this. Tell me if you want to hear more. Yeah?
And the second question is, as to the right of this random singlet phase, you have basically an Ising model.
Ising model. Another thing to take home, did you?
Oh, yeah.
Yeah.
For this ATLT state, so is the random singlet phase a spin-half singlet phase, or?
So the random singlet phase over here is a spin 1.
Okay.
Because if you go back to this diagram, now each side has two spin halves, right? So what we're saying is the soil is so strong that each side will connect with two singlets to whoever it wants to connect to.
Okay.
So it's a spin 1. So you go from gap, so like spin 0, to a mixture of spin half, spin 1, to spin 1. Was there? Yeah?
Sorry to keep slowing you down, but can you understand the statistics of level spacing?
The statistics of level space. So this is so I think random matrix theory was the way, but this was first derived. But I don't know how. So to me this is so much simpler. I never went back to see what the argument was for random matrix theory.
But do you have level repulsion in this model,
or? So this model is a localized model. So your level of repulsion is suppressed because
it's like Poisson.
So it's not. So yeah. But it's not exactly like Poisson, right? You have some level of attraction here. It seems like. Yeah.
So what's the strategy for like for the AKLT for higher spins? Do you use a similar one? Or?
Yeah, it's basically whenever you look at a two-side problem, now instead of having just singlet and triplet states, you have singlet, triplet, whatever, with the 5 states, 7 states, etc., etc. Whatever the proper words for those would be. So what you should do is whenever you have a strong bond, eliminate the most excited subspace. That corresponds to putting a single spin-half singlet between the sides. And then you can spread those around. But I can answer that question more, outside class, because this is not part of the. This is a rather advanced application of field space RG, which I'm happy to discuss because that was part of my PhD. But let's do it later. Other questions? So let me just make one comment since I already have Dyson Singularity here on the board. If you now add chemical potential disorder to your random spin, to your random fermion chain that you're supposed to diagonalize sometime, you can do that very easily on the computer. What you do by doing that is you lose the particle hole symmetry. So it is as if you lost your ability to focus your eyes on this needle sharp singularity. It just starts moving around. It gets averaged. It gets capped. And you end up with a finite density of states. That's Anderson localization from this perspective. So the chemical potential disorder is relevant, and if it's weak, then you can make this flow down to the scale of the chemical potential disorder. And at that point, you get a saturation of the density of states. And that's how you can see Anderson localization from this direction. This needle sharp singularity gets out of focus. Yeah.
So you're saying that if we take a model of spinless fermions in 1D with disorder in the hopping, we get this phase, the sharp phase,
That's right.
and chemical potential disorder gives
Right.
us.
Right. So I'll say this in equations since I'm driving you crazy with the same things. if you have this model for fermions, this will give you Dyson singularities. This is the thing that you can easily diagonalize. You can add a diagonal component to the matrix, mu I, ci dagger ci. So for spins, this is like a magnetic field. This will always win and will induce Anderson localization. And if I'm not mistaken, in the absence of this term, you get something that's called Lifshitz localization. And which brother? I don't know. But maybe Misha can say. So this Lifshitz localization, which of the brothers is it?
The one I showed yesterday.
That was my suspicion, yeah. So not Landau Lifshitz. I made a mistake. Okay.
His junior brother.
Thanks. All right, random bosons. So far I was discussing physics that, great names have figured out, and they were very lucky because the physics was precise. It was asymptotically exact. The significant randomness made disorder stronger and stronger as the RG progressed. Now, when I got to this field, a lot of these problems were already out and solved, so I had to settle for problems that are not as precise, not infinite disorder, one of which was random bosons. That's a very interesting problem that has been lingering for a while. Random bosons in 1D. And if you want to be less vague, I would say superfluid insulator transition. Of random bosons. All right. So Thierry talked about this, right? He showed you a bosonization model, a bosonization description of a line of superfluid that has disorder. And he had something like this, right? Disorder on the y-axis, Luttinger parameter on the x-axis, measuring interactions. So inverse application. I'll write it and reply in a minute. But let me just make sure that I'm doing this right. Yeah, inverse Luttinger parameter. And then he had this dome. A superfluid here, an insulator here, and he was looking at this corner. And he was showing you that you get Kosterlitz Talus flows like this, right? This is a corner of low disorder and interactions. Finite interactions. But there's a whole rest of the dome, in particular at high disorder, that was not clear. The methods that Thierry showed you were perturbative in the disorder, and disorder was relevant in a big chunk of the phase diagram. So one question that remained for many years was what happens when the disorder is really strong? Can you use this real space RG methods? And Raoul pushes me to write down Hamiltonian. I think that's a good idea. Let me draw a diagram first. I think when you have strong disorder and you want to discuss a superfluid insulator transition, it's nice to have a discrete model, right? Instead of having a bosonized action, let's write a discrete model. And I want to think about like a bunch of superfluid puddles. Actually, I am a solid state guy. So bosons are a bit of a stepchild for my physics. So I like to think about these things as superconducting grains with Cooper pairs in them. So often my language would be superconductivity. Let's think of a chain of superconducting grains that can allow Cooper pairs or bosons to hop between them. Plus, if you're thinking about superconducting grains, like think about like grains of lead, even if they're microscopic, even if they're nanoscopic, they're relatively big in terms of K Fermi, right? In terms of lambda Fermi. It means they have a lot of electrons. They also have a lot of protons, so they manage to become neutral. So you can think about like having measuring the number of Cooper pairs relative to neutrality, right? So in each grain, let's think of having an operator that tells us how many Cooper pairs we have in excess to neutrality. So number of particles, bosons or Cooper pairs, away from neutrality. And this is so Ni is not exactly the number operator you're used to, because it can also be negative. So you can have a deficiency of Cooper pairs, you'll have a positively charged grain. Now, but if I have a number operator, what else do I need? A phase. They're superconducting grains, right? They're grains, they're 0 dimensional, not really superconducting. But let's describe the phase of the superconductor. Well, how should I mark the phase? Ooh. How did Thierry mark the phase?
Why? Phi.
Theta. Thierry wrote theta. I'll write theta too. But I wrote this in the notes and I'll say it out loud. This makes me break with the tradition of my own teachers in the west coast of the US, who mark the phase of the superfluid with phi and the density with grad theta, which is the opposite of what Europe does, which is mark the phase with theta and the density with grad phi, which is what Thierry did last week. Now this was a source of a lot of tension over the years. I think that was the primary reason why Thierry wrote the book, so that his notation wins. And so, you know, in spirit of friendship in the school, I'll use Thierry's notation. And so write in the notes, you know, all of you disciples, all of the people in the audience who are disciples of Matthew Fisher will have to forgive me. It says the Santa Barbara notation versus Europe, as far as I can tell, you know, going up through the ranks. So theta I, this is a very severe choice, right? This is a very important choice of the physics. Theta I is superconducting phase, superfluid phase. Angle of each side. And now, I'm not writing Hamiltonian yet, because I first want to decide on commutation relations. But let me just say, so in this diagram, bosons can hop between nearest neighbors. And I'll mark it as Josephson junctions. In addition, each grain has a size, right? And that size can be random. The size determines the capacitance. And it will determine the charging energy. So with that in mind, let's just think for a second about these operators, Ni and theta I. What's the commutation relation between Ni and theta I? Theta? Yeah, right?
Sorry, two grains also have a mutual capacitance, right?
Ah, yes. So, no, okay. So in fact, you can put mutual capacitance in, and you can add it to the model, and we can do it later. It turns out to be irrelevant. I'll tell you why in Thierry's language. And since this was last week, I can do it without explaining anything, because presumably you know this fluently. So in Thierry's language, there was an interaction, right? The interaction was written in the bosonic language as grad phi squared, right? Yeah. That's like a self-capacitance, right? If you had to include mutual capacitance, it would have to be something like grad phi at some point x times grad phi at some point x prime, right? Which means that it will go like, right. So it will be like k grad phi squared. So it's like another nabla over here. Another nabla means another dimension of irrelevance. It means an engineering dimension that's one more irrelevant. And that's why we forget about it. And in fact, it'll end up being nabla squared just by symmetry, right? Everything else will go on to the grad phi.
Is this equivalent to making some assumption about
grains being much further apart than their size?
You can think about it that way for superconductivity, but you just expect that it's an irrelevant interaction.
Or closer than the scale over which the field varies.
Yeah. Well,
because that's the one.
Coulomb interactions are fairly long range. So if you push me against the wall and ask me to account for Coulomb interaction, I'll say, oh, it's probably irrelevant. I don't want to talk about it. But it's a good question. So from the bosonized models, we know that these things are irrelevant because they have a generic dimension 2 extra, if I'm not mistaken. So we forget them even in the random model. Now, for Cooper pairs, it might be important. It might drive you to a different universality. It should be checked. For bosons, the interaction is very local, right? The interaction comes from, it'll basically be within puddles, right? Into that? Should I explain this?
No, go ahead.
Okay. Let's forget about mutual capacitance. I'll tell you about the puddle picture a little later. And then you can see that for that, definitely, for neutral bosons, there is no long-range interaction. There's only contact interaction anyway. So that's okay. Other questions? Yes, sir? Okay, what's the commutation relation between n and theta?
I delta.
What?
I delta.
I delta.
Yeah.
So delta for different sites, right? So if we have ni theta j, even though this is the excess number, this is still delta ij times minus I think. But whether it's minus or plus, it's up to you. Now, working with n and theta means we're working with total variables, and therefore, I feel obliged to tell you how this corresponds to creation and annihilation operators of bosons. Should I do this? You curious? No? Should I skip? Any interest in creation and annihilation operators?
Just the convention.
No.
Psi is e to the
What?
Just the convention. Is psi e to the power I theta or minus I theta?
Psi, okay, so for this, let me write it quickly. Square root of n naught plus n operator e to the I theta. And this n naught is how many Cooper pairs I need for neutrality. And I assume that n naught is much, much bigger than n hat, and therefore I can write this just as square root of n hat e to the I theta. So from now on, e to the I theta is your creation operator. Okay, this is a bit of an unimportant detail. Nonetheless, I felt obliged to say it, because now I can go back and write a Hamiltonian. So what will my Hamiltonian be? It will contain two pieces, right? Hopping. What would the hopping look like? Any guess?
B dagger I, B dagger I.
Okay, B dagger I, Bi plus 1. But now I don't like the B's anymore. That's why I wrote them there so that I can forget about them.
Cosine theta I minus n hat.
Cosine. That would be the Josephson energy. Of course, the Josephson current is a derivative of this with respect to the theta. So the hopping would be a sum over I minus ji cosine theta I minus theta I plus 1. What other thing goes in the Hamiltonian? Charging. Now, charging is like capacitance, right? Q squared over 2c, no? So instead of writing capacitances, I'll write interaction energies. There's a different I, so I'll write a J here. There's a parameter U. And when I multiply it by ni squared, and well, this is Hamiltonian, so I'll put heads for just this equation. I get the charging energy. This is essentially Q squared over 2c, right? It's important because capacitance is something we understand, right? We know how to add capacitances in parallel and so forth. Let me make a quick side comment. Here, I assume that the neutrality point is sacred, right? You have an integer number of Cooper pairs on a grain. With a particular integer, it will be neutral. But it might be that there's some crap around, right? That will give you a random shift of chemical potential, right? And some people write it, everybody used to write it like this. Mu I, Ni, with mu I being random. This is not helpful. If you really want to solve this problem, then what you can do is say, oh, there's a little bit of an offset charge, Ni bar, and this is the interaction, right? So in order to be neutral, you have to have a fraction of the Cooper pair, which of course you don't have. But this amounts to the same thing, right? Because you can expand, and then Ni bar is like mu. So I'm not going to discuss this. I'm going to set this to 0 and look at one particular case of a superfluid insular transition. But if you're curious about it, you can read in the papers, N bar can also be anything between 0 and 1. That will give you a Bose gas. It can also be confined to a half. That will give you a different type of insulator. This is a tangential comment. I've been making too many tangential comments already. I'm going to leave it at that. But if you want to think about a random chemical potential, do it like this. But now we're going to not think about it. We're not going to think about crap wrong. So we're assuming that we have particle-hole symmetric charging interaction. If Ni is +1 or Ni is -1, we get the same energy. Yeah?
So if N bar were half, then you have to have an odd number of electrons on it.
Exactly. So it is as if you had an odd number of electrons in the original grain. So for superconductors, it kind of makes sense as a possible disorder. For some grains, you can have an extra electron. It's kind of curious because what you get in the end is a random singlet phase insulator. Yeah, Brian?
Sorry, just going back to this mutual capacitance. This isn't a short-range interaction, right? It's a 1/R interaction in many grains.
Yeah, that's why I said that if you force me against the wall to consider Coulomb interaction, then I'll have to say I'm sorry.
Okay, so is there anything I can do to assuage my fear a little bit that we're missing something important? It won't matter in the end?
You can pray, like I said. You can say that because it's so long grained, maybe it averages out, and you can take it in a mean field type way, like this. Or like some offset charge. That's randomly assigned locally, and of course it depends on fluctuations of long distances, but not very strong. But I think what you're driving me is, I think what I'm driven to say is that I don't know how to use real spacer G to handle a Coulomb class, which is really the problem that you're thinking about, right? But I know that there is an analysis like that, kind of, and there's definitely a new mean field analysis by Ariane Amir and company that kind of gives you some more intuition about that. So I'm not thinking about that possibility. So what I'll say, so that Brian stops, being concerned about mutual capacitance, this is sitting on a nice metallic surface that screens every Coulomb interaction not on the grain. And the distance to that gate is smaller than the distance to your nearest neighbor. However, it's larger than the size of the grain. So this combines Woodrow's comment into where this is well defined.
Good.
That's okay? So it relieves you of the need of praying. So this is a Hamiltonian. The physics of the disorder, Ji depends exponentially on the distance between grains. Is it clear why? So you can think of leaking wave functions, and wave functions decay exponentially outside the grain. Charging energy is like inverse capacitance, so it varies because the grain size is random. Now I'm talking about the superfluid insulator transition. And just so that we have reference, we can draw a line. J over U. Presumably when J is large, what phase do I have? Superfluid or superconductor, whatever. When J is small, what do I have? An insulator. In the superfluid, basically coherence is formed throughout the chain. And in the insulator, charge fluctuations are suppressed because there's not enough energy in the bond strength to create charge fluctuations and overwhelm the charging energy. So somewhere there should be a transition. And this is the transition that Thierry talked about. Can I access this transition from a strong disorder perspective? Large disorder in J, large disorder in U. Do you understand what we're trying to do? Okay, so can you guess how we're going to go about it?
Real space LG.
Real space LG? Good. So what do I need to do in real space LG?
Identify the strongest term.
Yeah, so let's define omega. So real space LG. Omega is the maximum of Ji or Ui. When we encounter a maximum, we need to do some kind of a decimation procedure, see how the distributions evolve, and hope for the best. Yeah?
I guess I'm slightly bothered by something, which is that it doesn't seem that this model is pathological when U is 0.
Pathologically what?
So normally you'd expect this model, because it's random boson, to be pathological when U is 0.
Yeah.
But I mean, can I see that?
Yeah, you can.
Oh, I see. Because
So let me tell you how. If U is 0 at one site,
yeah,
then there's nothing in the Hamiltonian that doesn't commute with theta on that site.
Okay.
Right? That means that you can make that theta be something,
yeah,
say 0, but theta equals 0 is like a voltage that's set, let's say to 0, right? Because voltage is the time derivative of the phase angle. Shows some relation. That's like you put a ground somewhere in your chain. The ground is ground, right? It's like you have one grain that's so large, it's grounded. But then if you connect two things through ground, they don't interact with each other. Right? So that's how you see it. So if U is 0, it's like the grain is so large, it's like a ground. And you can think about the right of the chain connecting to one side of the ground, the left side to the other side, they're very far away, they're fully screened in the way. They don't talk to each other. Yeah?
So you're saying that, so U is 0 in that case, right?
Yeah.
And
So it's infinite capacitance.
So there's no cost to moving theta, basically. Oh no.
No. Theta cannot be moved.
Theta cannot be moved.
Theta cannot be moved. It's like an infinite mass.
But there's no energy cost to moving theta, is there?
Cosine.
Cosine.
Oh, but that
No.
But
It's not that there's no energy cost. There's nothing in the Hamiltonian that's capable of moving it. It's like think.
Except that the other thetas.
The other thetas commute with it. So the situation is the following. So because n to theta is like momentum to x, this you can think of as cosine xi minus xi plus 1, or theta I minus theta plus 1. And this you can think of momentum, right?
Yes.
Like p squared.
Right.
Now, if this is momentum, p squared, u is like 1 over 2m. Right? So u going to 0 is like m being infinity.
So
if you have like a weight with m being infinity, no matter how much force you apply to it, it's not going to budge.
So when we are doing, so in the physical system, it would choose something, and every other thing will be tied to it through the GIs. Like the theta I plus 1 will set itself according to theta I and the bond, the bond between them. So the bond exists. It's like a magnetic field, maybe.
Yeah, it's like a magnetic interaction.
I see.
In the next
But
model.
it doesn't have any fluctuations. That's what you're saying.
That's right.
Okay.
So if you just had the cosine pieces, that would have been a classical XY magnet in 1D with no fluctuations.
But if I were doing a full thermodynamic average, not thinking about this, I would be averaging over all theta.
That's right. And you would have an interaction. But if you just ask, do the thetas move in each realization? The answer is no.
And it doesn't matter where it lies, because everything else can be rotated.
Yeah, sorry?
It's not obviously the same pathology that comes up in theory of if you consider three bosons in disordered potential, what happens is that all of them clump in like a single well, and that makes the energy insensitive to system size, etc., etc. So it's like it's very bad. Whereas here it seems like if I had no use, I'd have a classical model, but it's a well-behaved classical model.
That's right, because well.
So that problem is also here because you can shift the theta i's by 2 pi without changing anything, and every time you change it by 2 pi, you add an extra boson there.
No.
Right?
No. This is symmetric with respect to 2 pi rotation. The Z1 symmetry.
I mean, it can be
the
understood.
Z1 symmetry and it's periodic.
I mean, it can be understood if GI is large, because then if you, but that is the limit we're talking about.
Yeah, I mean, GI large, GI small, it's the same thing.
But then basically all the theta i's around the very large grain are going to be locked to it. So maybe that's similar to.
No, I mean it's not.
Yeah,
it's
it's
not
right.
pathological. It seems well behaved.
Yeah, but also, so I mean, I think what. So when you have a puddle that's not interacting, right?
Yeah.
It's not interacting approximately, I guess. Meaning you have a Bose-Einstein condensate, right? Eventually you'll have I-orders, interaction, etc., that will regularize it.
That's what I mean. I guess I'm not seeing. I guess.
Yeah, oh, I know what's the issue. You could have any number, and that means that theta would be well defined, right? If theta is well defined, E to the I theta is well defined. That means that B dagger has an expectation value. That's a Bose-Einstein condensate, right?
Yeah.
Even what you described, there's no instability. There's just a Bose-Einstein condensate.
Yeah, exactly.
Right? An attraction would give it an instability. So a U negative would give it an instability. So in that sense, it's the same thing. U equals 0 means the theta corresponding to that site is well behaved, classical. When E to the I theta is classical, that means a Bose-Einstein condensate.
Right, but I guess for maybe this is an issue with how chemical potential behaves in two different models, but
yeah, but let's discuss this later. But I think that's hidden in this environment. Yeah.
I'm so confused. It looks in the Hamiltonian like Jerry's limit would be J goes to 0 with U finite, because then everything would clump at whatever site has the smallest U, I guess.
Can we get on?
Let's get on. And let's discuss the correspondence with Thierry's model a little later. But I mean, if just quickly, because you did see Thierry's model. Cosine theta I minus theta I plus 1. If you expand in powers, the cosine, you get a gradient of theta squared. Now, n, I said, is like grad phi. N squared is grad phi squared. There you go. This is a discrete model of bosonization. Let's move on, because I have been spending a lot of time on tangents. So let's analyze this model, and then we'll understand it, then we can go back a little bit and talk about connections. What should we look first, J or U?
J has more spread, probably, but whichever is bigger.
Yeah, so I mean, we're looking for the maximum U in the chain, right? We're looking for the smallest grain. Really? No, it looks like this is the smallest grain. Let's call it grain N. Now, if this is the smallest grain, it's not going to participate in any superfluid that will form, because charging fluctuations on it are going to be severely suppressed because of the charging gap. Then let's set the number on it to something. What? So how many X's Cooper pairs will have over the neutrality? None. Let's set it to 0. Let's say, let me write here. So decimate UN, which is the largest scale of the Hamiltonian. Then I can write like we did 2 days ago, H naught. The biggest piece in the Hamiltonian is UN, NN squared, right? So for this, I know what the ground state right away. What the ground state is right away. I can write a graph of the energy as a function of the energy as a function of n. There's a very nice point here with 0. And there are highly excited points with +1 and -1. What is the ground state? 0. So this is not the true ground state of the system, right? Why? You have J's, right? So the J from here and the J from here want to create fluctuations of the charging here. Of course, they're suppressed, which means that they'll be virtual. But that means that we can take care of them in perturbation theory. So I think of a perturbation as V being n minus 1 minus theta n, Jn cosine theta n plus 1 minus theta n. Now, in an animation, what these guys do is they take the Cooper pair, they hop it to here. That's a virtual excitation. It should be relaxed. It's relaxed by Jn hopping it on until it ends up inside n+1. So we can take care of it with the usual second order perturbation theory. We know the second order perturbation theory, the way I write it is terribly complex, so I'll take a new board for it. I want to describe this process of co-tunneling between n minus 1 and n plus 1. And I'll use this formula that we had, which was we start with the ground state, right, of site n, so 0 particle on site n, 0 axis particle on site n, have the potential, sorry, the perturbation, V. I need to add up over all excited states. All excited states, so Nn should not be 0. And I need to divide by the energy of the ground state of grain N minus the energy of the charge grain N. And I'm writing the number of the grain, sorry, so I should write it like this. Number N of the grain N can be anything, +1, -1, +2, -2. Is it clear? Am I losing you? Okay? Let's take an example of what?
What is summation on?
The summation is on the N that sits in there. So let's look. I mean, V has a lot of terms. It has 2 terms as written here. And it's nice to also break the cosine into 2 terms. Into the e to the I, theta n minus 1 minus theta n, and then the complex conjugate. Let's just take one of those. Let's take the term, say Jn minus 1 over 2, that hops a particle from the left onto the grain. So I'm just choosing to look at this term. I can do this to all other terms. And by all other terms, there could be a Jn here, there could be a minus here. Now, e to the minus I, theta n minus 1, removes a particle from grain n minus 1. E to the I theta n creates it on grain n. That's a crime. It's a crime because we have to pay an energy penalty. So this can be this connects us with one particle in n. What's the energy denominator? Omega.
U.
Un, right? Which is omega. With the minus. Right? Notice that V has a minus also, minus Jn minus 1, minus Jn, but there's two V's here. So I don't need that minus. Now, I want a term that will relax the charged nth grade to a neutral nth grade. And I want it to be the coming from this bond. Now this bond is Jn, this bond is Jn minus 1. Okay, so to relax this, I need to create a particle at n plus 1 and remove it from n. That will get me back to 0. It's okay? Yeah?
So by saying that you first look at the maximum of the largest UN, you're basically placing yourself in the insulating phase and starting from there?
No, so I'm saying that that particular grain is an insulating element. It's hurting our cause of superfluidity. It's going to be very hard to charge it. We'll remove it.
But, you know, this omega is defined as the maximum of Ji and Ui. So you could have chosen to start with eliminating a large Ji.
Oh.
And so then you would have started from the superfluid phase.
No, let me clarify. The problem goes like this. You invite me to look over your chain of superconducting grains. And I'm a disorder expert, so I look at it. And I try to find the maximum. I try to write a description of that chain in terms of Hamiltonian like this, ignoring mutual capacitances. And then I'll make an ordered list of all the U's and J's on the same footing. And I will see, okay, maybe the largest coupling in your chain is a U, U10. Maybe the next one is J25. Maybe the next one is J14, and so forth and so on. So I need to make a strategy for decimating either a grain, either a large U, or a bond, a large J. And I don't know a priori which I'll do more. Of course, if I do more J decimations, meaning more of my J's were large, that will bias me towards the superfluid. If I make more U decimations, that will bias me towards the insulator. But I need to know how to do both.
So here you're just starting with one, and then we're going to do the other.
Then we'll do the other? Yeah. And then we'll see how each of those make the distribution of effective J's and effective U's change. And then we'll find a phase diagram. Is it clear? Sorry.
Yeah. I just thought that you just had decided to start from the insulating phase or whatever.
Yeah, no, it's a great question because until now we talked about the single phase, right? Eisenberg model is this random single fixed point, there's no competition. Here we're at a situation where J and U compete. And each one wants to poo-poo the other. And the question is, who does it better? So you need to understand both. So we start with U because U is actually simpler. All right, so what do we get here? Now, just from this term, we get, okay, e to the I theta n connects that state. And the same here for the e to the minus I theta n. Actually, I screwed up a little bit. What did I screw up? So I need to read this from the right to the left. What? It doesn't matter, but there should be a minus sign here. So if I read it from the right to the left, e to the minus I theta n would actually take away a particle. So I would have to write -1 here. It really doesn't matter. But I'd like my equations to be correct. So I can either put a minus sign here and here, or here and here. It needs to be right. You with me?
Yeah.
All right. Okay, enough. It's not a great day for calculations on my part. What do we get? J to the left j to the right over omega. Ooh, familiar. We also get 1/4 because of these 2's. That 2, and there should have been a 2 here, because I broke the cosine. And then I have e to the I theta n minus 1 minus theta n plus 1.
Negative sign.
What?
Negative sign due to minus.
Minus,
No, negative sign in front of.
negative sign. I need that negative sign. Yes, there's a negative sign from here. It's good, because there's a negative sign here, which I had better reproduce. And I have other terms. Let's see what other terms. Opposite process? Okay, good, because that will combine us into a cosine. Also, what another term? What other term?
Energy shift.
Oh, they are now back. So replace these, right? So that will give me a factor of 2. So in the end, I just get jn minus 1, jn over omega times cosine theta n plus 1 minus theta n with the minus sign. Everything works out to give me exactly what I wanted. Let me, oops, that's not good. Wanted to blot this out, but there's a ghost of a side there. That side mediates an effective Josephson coupling and minus 1. Thank you. I get a Josephson coupling whose value is jn minus 1 jn over omega. So far so good. This is exactly the same as the Eisenberg model, no? What? Without the 2. It's like the XY model. That's right. So what did we do in this step? We had a very small grain. We said that small grain is going to pour superfluidity. It's not going to get charged. We can just set it to be not charged. Work with perturbation theory to see how, if we normalize this, it produces a coupling, an effective coupling between its neighbor to the right and its neighbor to the left. We eliminated that site. We reduced the energy scale of the Hamiltonian. We're good. We reduced the energy scale also because we know that this quantity is much smaller than jn minus 1 jn omega. Questions? Yeah. What?
There's also the possibility of the Cooper pair jumping back, right? Also in second order.
Yeah, so that's why we have a cosine. So a cosine contains this, but it also contains the negative.
I thought the other sign is just for hopping from the other side.
I think he's asking about the energy squared.
What?
Yeah. For
hopping there and back.
Yeah.
Oh, absolutely. But then what? That's there. What operator will it come with?
Something over omega.
No, operator. Identity. It's an energy shift. So it won't change the phase. So I'm ignoring it deliberately. There will be a jn squared and a jn minus 1 squared shift of the ground state energy. Yes, Mark.
Implicitly, it seems like a local chemical potential shift, right, rather than a global chemical potential shift. Because if I
What, the jn squared?
Yeah, because you know.
No, it's no. It's not a shift. It's an identity. It doesn't come with an n in front.
If I were working with the sort of microscopic BI, imaging perturbation to the BI, it seems like I'd get sort of, I'd get a BI plus 1, dagger BI plus 1. Some cosine takes that.
Right. So what you're saying is that you'll produce a little bit of a. So if you take into account the square root of n,
yeah,
you'll see a little bit of a shift.
Yeah.
Yeah. Yeah, that's true, and that will be a suppressed thing. Yeah. Mm-hmm. Questions? Okay. But actually, it'll be with an absolute value of the number, I think. So, well, no. Yeah, no, you'll have an operator there. But within the rotor model, strict rotor model, you don't have it. Right, so it'll be also suppressed by 1 over n0. Other questions? So we're about to get to break. Let's just do the concomitant rule. What happens when we have a large j? This is great because the large j step is kind of more touchy and less precise than the large u. But of course you won't be able to ask me too many questions about it because you don't want to go to break. So okay, so let me erase here. So suppose the largest element in the Hamiltonian is now a j. So decimate Jn. That means that I have two grains that are of moderate size, and they're really close together. So there's a term minus Jn cosine theta n plus 1 minus theta n. This is side n, this is side n plus 1. It's really large. It's really large. What do those two sides want to do?
Same phase.
Lock their phase, right? By locking the phase, actually it means they want to do this. That means that the phases would be locked without the possibility of making a phase slip by 2 pi. So this would make a superfluid cluster. But now I will even say more. I would say that a good approximation, or an approximation that I would like to make is that this is 0. Or sorry, that
minus j.
Theta n equals theta n plus 1. Yeah?
So did you explain the cosine there?
Yeah.
So there is 1 minus x squared.
Oh, sorry. So I wanted to. Yeah. So and I'm dropping constant terms.
Why are you saying that there's no phase slip?
What?
Why are you saying that there's no phase slip of 2 pi? I mean, you can have like phi n equals to pi n plus 1.
No, so the Hamiltonian itself has it, right? In it. Right? The charging interactions can make these phases fluctuate and they can create phase slips, right? But what I'm saying is that because Jn is large, the amplitude of such phase slips is going to be tiny. In fact, the amplitude of such a phase slip is going to be proportional to e to the minus square root of Jn over the u's around it. So my approximation in this real spacer G is a little different than saying that I have a gap and I'm sticking to the ground state. It's more like saying that the amplitude of phase slips is 0. Because I know what it is, I can calculate it from bosonization. But I mean, it makes sense. No, this term is large. The phases lock. And you have a superfluid cluster. Yeah?
I remember something like critical temperature in XY model that you cannot do this approximation anymore, which is called Koster-Salas transition temperature. So if you're above this temperature, you cannot. Can you still do this in this one-dimensional model?
Yeah. So first of all, so what Thierry showed you is a Koster-Salas transition that happens at 0 temperature, and I'm showing you a different analysis of the same system at large disorder. Now, the Koster-Salas is indeed a proliferation of phase slips in one dimension. What I'm saying is that this bond, so in 0 temperature, it's not about temperature, it's about action. It's about the amplitude of the process. So I'm saying is that, as Torsten made me say, the amplitude of the space they process is very tiny. It's very tiny on this bond. It's less tiny everywhere else in the chain, right?
So this is another way of saying that your excitations will be long wavelength excitations.
No, this is another way of saying that if we destroy superfluidity, it won't come from this bond.
Can you say that?
Superfluidity is destroyed due to phase fluctuations. Those phase fluctuations will not be on this bond. There will be other bonds that will be the culprit. So we're neglecting the possibility that superfluidity is going to be destroyed because of this bond.
I don't want to interrupt the topic.
Okay. Is it clear what I'm saying? Basically, like saying you have a very good electrical connection between two grains. Okay, if that's the case, there's still a problem because there's charging interactions that are different than these two guys. Right? Charging interactions I can describe as capacitances, right? To ground. This would be Cn plus 1. This would be Cn. If these two grains form a single grain, what's the total capacitance in that grain?
Sum of U's.
Sum of?
U.
No.
Sum of C.
Sum of C's.
Okay.
Right? So this tells you that the effective capacitance of n and n plus 1 cluster is Cn plus Cn plus 1, which tells you that the interaction energy inverse. 1 over U effective of n plus 1 is 1 over Un plus 1 over Un plus 1. So what did they do? I said the two grains are so strongly connected that you might as well think about them as a single superconducting grain. If it's a single superconducting grain, I should think about the total capacitance of the grain. Capacitance is in parallel. You can think about the surface area of the capacitor ending up. They add up. Interaction energy ends up like this, adds up like this. Now, it's like resistance in parallel, right? A resistance in parallel is smaller than either of the resistances. So U effective is smaller than either Un or Un plus 1. Yeah?
Why are the capacitances not in series? It looks to me if I go from round to round.
Yeah, because my diagram is kind of crappy. Here's the diagram again with some room underneath. So we made a cluster.
Ah, okay, yeah. Okay.
Right? It looks like this.
So, okay. So, yeah, convenient.
No, I won't rush to conclusions. Right, so it's like they add up.
Yeah.
It's a very intuitive step. Now, I was being a little cagey about this step. Why? I think this is good. This is good. I took an amplitude of facets and I set it to 0. It's very tiny. It's exponentially suppressed, assuming strong disorder. However, this step is a little touchy. Because I said, well, I locked the two phases, which means like I put a spring between them. They cannot go too far away, but they can still fluctuate. If they fluctuate, well, let me look at this diagram. There's a Josephson junction that connects site n plus 1 with site n plus 2, right? That Josephson junction does not look at the average phase, or the center of mass phase of this cluster. It looks at the phase of n grain n plus 1, which is not exactly the average of theta n plus 1, or the center of mass coordinate. But by assuming this, I can say, this is just the center of mass coordinate, and everything is connected to this. So I'm neglecting fluctuations within the grain. But then you can ask, how big are those fluctuations? And they're suppressed with a term that's kind of like this. They're suppressed with a term so it will give you a suppression of the bond, of this bond, that looks like this. So again, if Jn is large, this is 0. and this is 1. And this is the Weierwälder suppression. Yeah?
How is it different from doing the other ground state assumptions?
The UN?
Yes.
Oh, UN is well defined, there's a gap. Here there's no gap. So you can have charge fluctuations of Cooper pairs sloshing freely back and forth, which corresponds to fluctuations of theta n minus theta n plus 1. And those I want to neglect. And I'm saying that the thing that controls this neglecting is saying that this thing, which is like, you can think about it as the, this thing, which comes from just thinking about fluctuations of this relative coordinate, is small. So the fluctuations of this relative coordinate are very small, as long as Jn is much larger than E.
So these will not show up in, let's say, finding out whether the full thing is a superfluid, but it might show up in the spectrum. But
exactly. So what it does, it will force me to renormalize also the bonds coming out of this cluster by multiplying them by a factor like this.
I see.
Actually, it's better. It's 1 over 80. But this is very close to 1, so I forget about it. Yeah, sure.
So I think the question about like expansion, do the expansion around about cosine, has the problem about 2 pi thing doesn't occur here is due to the fact that we are dealing with one-dimensional situation, and for 2D there may be vortices, but
yes.
Here 1D there's no such case, and
yes.
that's why we don't have such problem.
It's so subtle. So the way the superconductivity is destroyed in 1 dimension is because even though you have these cosines, phases fluctuate by 2 pi. If you fluctuate by 2 pi, it doesn't cost you any energy. But it's just like tunneling to this potential. It's like you have, you can think of the wave function for theta n. It has a landscape like this of energy. It wants to sit at the bottom of that potential, but it can tunnel through this potential because of quantum effects. Because of quantum effects, operator in the Hamiltonian does not compute with it. But you can think about like a WKB amplitude of tunneling through a big potential, right? Should be like e to the minus gap times some distance. It's easy to convince yourself that it will be this. Yeah,
and so far we always had like the case that the new coupling constant is much smaller than the old one, but now we end up with something which is of the same order. It's not like creating more and more disorder as before. Does it like get us into trouble?
It's not great. It gives you a period of doubt before you actually solve for the end. So yes, this is kind of a screwy G condition. It reduces the energy scale, but not by much. By a factor of 2. So I could say a factor of 2 is also already good, right? If UN and UN plus 1 were the same, we reduce it by a factor of 2. That's the worst case scenario. The factor of 2 is modest. It's not asymptotically going to a factor of infinity, but it's good. It's a good start. Now, the thing is really that this rule will not generate infinite disorder. And in fact, we'll work out tomorrow the universal coupling distributions that these RG rules imply. And we'll find out that they're not infinite timeless. And then you will have to ask me some hard questions. Why do I think that this is good? And you're already starting now, so that's not bad either. But then we'll